Alright, so we will have a relatively shorter lecture today. By that I mean we will finish at 3:15, which is the regular time. Yeah, because I have other things to do at 4 o'clock, so I need to leave at 3:15. Okay, good. So let's start. We'll quickly recap these two DIYs. Hopefully everybody is able to prove these. They are not too difficult. What we will do is we will assume these because they were DIYs, and we will use this to observe a complete characterization of separating cuts in bipartite graphs, in bipartite matching code graphs. Right? And hopefully you also figured that out, but we will anyways just quickly go through it. Basically, this has all of the power. Once you have this, everything just goes through very smoothly. Okay. This is perhaps one of the simplest proofs I have seen of characterization of separating cuts in bipartite graphs. So, what does it look like? Did anybody figure out? Well, those of you who did not already know before, any ideas on how a tight cut would look like in a bipartite matching code graph? Raise hands. Any ideas what it would look like? You can give an example and then explain what your example is saying. Just an example will work. Yeah? You want to give an example?
I mean, I have a general picture in mind.
General picture is also fine. From the mind to the board, if you don't mind. Yeah, anywhere is fine.
So, now given a bipartite graph, so this is let's say A and B for a bipartite graph.
Mm-hmm.
There's edges like this,
Mm-hmm.
and there's edges like this, and this is a right. So
Yeah.
going across in some sense.
Sure. And can you also talk about the cardinalities of those sets, or there is no such
this
thing?
Will be exactly difference is exactly one in both sides. So this is
Okay.
Let's say.
So which one is the bigger one? Can you mark the? So let's say this is your x, if I may. So let's say this is your cut.
Yeah.
This is partial of x, and let's say this side is x, and this side is x bar. Can you label the x plus and x minus?
So this is x plus.
That is x plus. That is x minus.
This is x bar plus.
Yeah.
X bar minus.
Cool. Yeah. And you are saying that all the edges in the cut go from the majority to the majority.
Yeah.
There are no edges between minority.
Yes.
Yeah. Yeah. Okay. Thank you, Deep. All right. Does everybody agree with this? Yeah. Does everybody get something along these lines? This is what a tight cut will look like in a bipartite matching code graph. Right. Let's do a concrete example while we are at it. So here is a nice concrete example. Yeah, it's a two connected cubic graph, therefore it is matching covered. And that's your tight cut. And those are the edges going from the majority to the majority, right? Let's label everything. This is your x plus, x minus, x bar plus, x bar minus. Putting this plus and minus at the bottom is an interesting choice because if you put x bar minus here, it looks very strange. So that's the only reason to go at the bottom, not at the top. It's because of the x bar minus. Yeah. Okay, so that's what it looks like. And let's see, so we'll write this down. Let's write down all the important points. So this is going to be our theorem 4.8. This is a characterization of separating cuts and also of tight cuts in bipartite matching covered graphs. So the hypothesis is GAB is a bipartite matching covered graph, and C partial X is a separating cut. Then the following holds. The majority part of X plus has exactly one more vertex than the minority part, and likewise the majority part of the X bar is exactly the minority part, and of course I messed it up, plus 1. Yeah. Okay. That's one point. C is a tight cut. We assume that it is a separating cut, but once you have this drawing, it is easy to see that it's also a tight cut. Yeah. In any perfect matching, you can use only one edge of this type because of the cardinalities being different by 1. So it follows that it is a tight cut. What else? Yeah, I mean X plus and X bar plus, it is cleared actually, but I'll still spell it out, are subsets of opposite color classes. So one will be a subset of A, the other will be a subset of B, and finally all the edges of the cut go from the majority to majority. Maybe I'll say each edge. Each edge of the cut has one end in X plus and other end in X bar plus. And let us observe quickly why this is an immediate corollary of this. See if you can observe it yourself. All you need is this fellow. If you just apply this, you will get everything here. Observe that it also works for trivial cuts, but in the case of trivial cuts, it is trivial. So it is interesting only when it is a non-trivial cut. And so you can assume it is a non-trivial cut. So both shores have at least 3 vertices that you can assume. And now just apply this proposition, you will get everything. Remember, a special barrier is a barrier for which you get exactly one non-trivial component in G minus the barrier, right? And in particular, what we have here is these are special barriers, both here and in the abstract drawing. So you can add one more point here. C is a tight cut and a special barrier cut. Oh well, special can only come when it is non-trivial. That's the reason they did not put special. So if you assume this is a non-trivial cut, because you need one non-trivial component, otherwise it's not a special barrier. So in the case of non-trivial, you will get a special barrier cut with respect to 2 special barriers, X plus and X bar plus. Both of them will be special barriers in the case of non-trivial cut, and this is a special barrier cut. Yeah. So therefore all these concepts, tight cuts, separating cuts, barrier cuts, special barrier cuts, they are all basically the same in the case of bipartite graphs. For special barrier, you need non-trivial. Once you assume non-trivial, then the definition of course works. Yeah. Good. Is everybody convinced that you get this as a corollary of this? Yeah? No? Let's look at the hypothesis. You have a separating cut. Trivial you can all check, right? Trivial is fine. Observe that trivial cut satisfies all these conditions. One majority will be single vertex, minority will be empty, and the rest of the vertices n-1 will be the other shore. So trivial cut satisfy. So assume it is a non-trivial cut. So therefore this hypothesis holds for both x and x bar. This hypothesis holds for both x and x bar. What is the conclusion? X plus is a special barrier of G. So x plus is a special barrier. So let me put 4 vertices, why not? Then I will have 3 isolated vertices. If I apply to the x side, and I get this picture. If I apply this proposition to one side, I get this drawing. Okay? And because it is a special barrier, this is a special barrier, so all the edges go from here to the outside. Now apply the same proposition to the other side. And you get exactly the same kind of thing. If I apply it to the other side, I basically get the same situation, and now all edges in the cut are incident here. Well, therefore all edges in the cut go like this. You got basically everything. The fact that it is a tight cut is just a counting argument. Right? Yeah, in fact, Lucchesi-Murthy basically leave this as an exercise, 4.8. They say that, yeah, just use 4.6, 7, basically just 4.7 and get everything from there. Yeah.
So this implies that there does not exist a barrier that could give us more than one non-trivial component. Bipartite matching program.
No, that is not true.
Okay.
That is not true. Yeah, so you can have a barrier which will give you more. Let me think. No, you can definitely have a barrier which will give you more non-trivial components. To see this, see if you can construct an example using splicing. Use splicing to construct an example. Yeah, so that is not what it implies. Yeah. The reason it doesn't imply that is because we just started with a separating cut. And then we concluded that this separating cut is indeed a special barrier cut. That does not mean that for every barrier it will be a special barrier cut. There is some barrier for which it is a special barrier cut. But there may be some other barrier for which it is just a barrier cut, but not a special barrier cut. Yeah. Just use splicing and construct an yeah, I'll just leave it as a DIY for now. And by the way, Piazza is active for everybody, so feel free to post and discuss on Piazza, right? So DIY, construct a bipartite matching covered graph that has a non-trivial barrier that is not special. Does anybody want to show an example? Yeah?
Let me think.
Okay, think. Anybody else? Basically, your best friend for constructing examples is splicing. After that comes bisubdivisions. But bisubdivision is just splicing with C4. construct an example?
Actually, even so I was trying to construct some complicated example using splicing, and then I realized even simpler examples work. So for instance, a large even cycle, take two vertices separated by an odd distance.
In an even cycle, okay, don't need to even do splicing, or just repeated splicing with C4.
Yeah.
Large even cycle. How large? 8 vertices?
That should do.
Yeah, 8 vertices generally works. So you want to take two vertices? Diagonally opposite, U and V. This is a barrier because it leaves out exactly two odd components, each with 3 vertices, and it is not special. Right? The point is, the corresponding tight cuts can be viewed as special barrier cuts. So one of the tight cuts you will get is this one, corresponding to one odd component. Although it is not a special barrier cut with respect to this special barrier, it is a special barrier cut with respect to another special barrier. What should I include? I should include something else in UV. UV and this one? W. Now observe, it is a special barrier UVW, and that cut is a special barrier cut. So it works. Yeah. Good. Yeah, this is a great question. Alright. Any other questions, concerns regarding the statement and its proof? All okay? So what we have is a complete characterization of separating cuts, tight cuts in bipartite matching choreographs, and they are the same. Right? Okay. Good. Alright, so there are a bunch of corollaries, but in the interest of time I will probably not mention them today. Let's forget those. Anyways, they are not going to be used today. So let me just skip. You can think about the consequences. I will give you a hint. Think about consequences with respect to two vertex disjoint odd cycles. Apparently there are some consequences. TIY. Think of some, these should be one-liners, right? They are basically corollaries. Think of some corollaries. And the hint is they have something to do with vertex disjoint odd cycles. Pair of, just two, not more. Okay. Anyways, I'll just leave it as a sort of vague TIY. You can think about it. There is no correct answer. Perhaps many correct answers. Who knows? Okay. Fine. So that's all for bipartite related stuff. Now I want to move to another very interesting result that I was not even completely familiar with until recently, or if I was, it had somehow gone very deep somewhere. So let's talk about some very trivial things first. A tight cut could have a single edge. I'll call it a tight one cut. Is that okay? K cut means a cut with K edges. So tight one cut means tight cut with one edge. What is the only example where this happens? Tight cut with a single edge, K2. Okay, that is a barrier cut. Yeah. One vertex is a barrier, the other is the odd component. Sure, fits the definition. Okay. What about tight two cuts? Can you all think about a tight two cut? Is a tight two cut also a barrier cut? Tight one cut is barrier cut. What about tight two cut? So tight two cut, what will it look like? Two edges. This is odd, although I have drawn it like even. This is also odd. Oh yeah, good. I forgot that we are recording. Let me draw it here. Thank you. So let's think about a tight two cut. Okay. Okay, so odd, and two edges. So this is my tight to cut. Do you all agree that the two edges are non-adjacent? Well, if they are adjacent, that is also possible. But if they are adjacent, then what does it mean? If they are adjacent, then what can you say? Then it is a trivial cut. Is that right? Is that what you're saying? If the two edges are adjacent, then the common vertex is a cut vertex, unless it is the only vertex in that shore. Therefore, it is going to be a trivial cut. Trivial cuts are anyways barrier cuts. All trivial cuts are barrier cuts. Yeah, the vertex is the barrier, the rest of the stuff is the odd component. Matching chord graphs are two connected, so yeah, except for K2. Yeah, okay, cool. So if the two are adjacent, then it's not interesting because it's a trivial cut, therefore it is a barrier cut. So let's consider the non-adjacent case. Now is it a barrier cut? These are my two edges, E and F. They are non-adjacent. In other words, EF is a matching. Now is it a barrier cut? Can you think of a barrier such that this would be the corresponding barrier cut? UT. UT is a barrier. Two vertices, I delete them, I get two components. Are they odd components? Are they even components? They are even components. Right? They are even components. Because this is an odd number of vertices. So if you delete U from here, you are left with even number of vertices. So UT doesn't work. Something else works? U and S. U and S works. Delete these two vertices. You get two components. Is that correct? Yes.
But it's a barrier. It should be like they should not be adjacent.
Right, they won't be adjacent. Because it is a barrier, they will not be adjacent. You're right. Right? Yeah.
So you have to prove that they are not adjacent.
No, I don't have to prove it, right? I know the graph is matching covered. So therefore it is going to be non-adjacent. You just proved it. You just proved that they are non-adjacent because the graph is matching covered. So it is a barrier you proved, and we know in a barrier it has to be stable. So you actually proved that they are non-adjacent. Yeah, you're good to go. Yeah, okay. So this is in fact the desired barrier. You delete these two vertices, and definitely you get one odd component. Therefore by parity you get a second odd component. Its vertex set is exactly this set minus U and S. Remember this is odd, so there's at least one more vertex here apart from U and S. Yeah. So this is a barrier and this is a barrier cut. So what we just discussed is tight one cuts and tight two cuts are barrier cuts. Easy. Turns out we can go one step further. Tight three cuts are also barrier cuts. Okay? So we'll prove this today. It's a nice it's a very nice proof. In fact, I'm going to try a slightly different style, motivated by my recent discussion with Vibhu. Yeah, I'll come to that. So we'll discuss a proof of this. Yeah? Okay?
This
Yes.
also shows that tight two cuts are also two suppression cuts.
Tight two cuts are also two suppression cuts because what was suggested earlier, U and T. U and T is a two suppression. Its deletion gives us two even components, and one of the even components is sitting here. Along with U, it is a two suppression cut. Yes, good point. So tight two cuts are both barrier cuts and two suppression cuts, depending on how you view it. Either you take UT, then it's two suppression. If you take US, it is a barrier cut. Yeah. Good. Any other questions, concerns? Okay, so if not, we will switch to the other side. We can take a 2 minutes break and continue. Thank you. Okay, is it recording? Thank you. Okay, so for the rest of this lecture, we have roughly 40 minutes. We shall try to prove this statement. In any matching covered graph, every tight 3 cut is a barrier cut. Yeah? And you will see some consequences of this in upcoming lectures and some assignments. Right? So the reason I like the proof is, one, because I did not know this before, so I just learned the proof this morning. And the second reason I like it is because it's really cute and it gives us a chance to exercise a bunch of things we have already observed or proved. Right? So we will use several facts we already know. Okay. So in the earlier case, we looked at tight 2 cuts and we considered 2 cases. Either the 2 edges are adjacent or they are non-adjacent. Right? So we'll do something similar here. Let's make a drawing. So let's say I call the edges E1, E2, E3. Sure. U1, V1, U2, V2, U3, V3. I probably don't even need the E labels, but anyway, it's fine. Let's say this is X, this is X bar, this is a tight 3 cut. Okay, E1, E2, E3 is our tight 3 cut. That means it's a tight cut and it has 3 edges. So of course, one possibility is that some of these vertices are actually the same. U1, U2, U3 all could be the same, or 2 of them could be the same. What's the simplest case? Let's deal with the simplest case, or what seems to be the simplest case. What do you think is the simplest case? U1, U2, U3 are all equal. If they are all equal, then do you all agree that it is a trivial cut? Otherwise, you'll get a cut vertex. Yeah? So if U1, U2, U3 are all equal, or V1, V2, V3 are all equal, then it is a trivial cut and it is a barrier cut. We are done. Right? So if U1 equal to U2 equal to U3, or V1 equal to V2 equal to V3, then C is trivial, thus barrier cut. Done. Yeah, this case is done. Now what may happen is, maybe only 2 of them are the same. Maybe U1 is equal to U2, but U3 is distinct. Let's deal with that. Supposing U1 is equal to U2, yeah, sure, this is correct. And then I have U3. In this case, what do you do? Can we conclude in this case also that this is a barrier cut? Does anybody see a barrier for which this would be the corresponding barrier cut? Right? I've only labeled 2 vertices for a reason. Do you all agree that that is a barrier? Those 2 are a barrier. Yeah? So works. So in fact, if U1 is equal to U2, which is, let's say, otherwise. Otherwise is a nice word. If u1 is equal to u2, I'm still done. Then u1, u3 is the desired barrier. We are done. Yeah? Okay. So the only case that remains is that these three edges comprise a matching. u1, u2, u3 are distinct, v1, v2, v3 are distinct. That just means this is a matching. Otherwise, that is, the cut C is a matching. When you are taking a whole course on perfect matchings, it is very common to use matching to mean perfect matching. Please don't do that. If you mean perfect matching, write perfect matching. If you write matching, I will assume it is matching, not perfect matching. Yeah? So, yeah. But the whole course is on perfect matching, so I understand why it happens. But I also want you to be alert to not make it happen. Right? Okay. So C is a matching. So in this case, we need to finish the proof. This is the hardest case, as you would imagine, as you would expect. So this is the drawing. Okay. We want to prove, so now I'm going to take the following approach. So this is inspired by my recent discussion with Vibhu on structural graph theory assignments, where he was asking, how do you come up with this sort of an idea, or how does this strike to you, blah, blah, blah. So my suggestion was, sometimes you assume the statement you want to prove is true, and you try to work your way backwards from there. So I will take that approach here. Right? I know the statement is true because, well, I know it is true. I read the proof this morning. And typically the book by Lucas and Murthy probably does not have major errors. So we want to prove that this is a barrier cut. That's our goal. So let's try to imagine let's try to figure out what that means. Right? So I'll try to write down the proof from the other direction. The goal is to conclude C is a barrier cut. This is my last statement of my proof, right? This is it. Okay, so let's assume it is true. What does that mean? That means that there is a set of vertices B, and when I delete that set, I should get this cut, right? But remember what a barrier cut is. Let's just make a drawing of a barrier cut. These components need not be trivial or non-trivial. I'm not indicating anything. Supposing this is my barrier, then this cut should be something like this. It should correspond to one of the odd components after deleting the barrier. Yeah? That means, what can you conclude? This component, its vertex set, what should its vertex set be? Supposing this is my barrier and I get this component J. What can you say about the vertices of J? That should be equal to which set over here? X or X bar? Either X or X bar should be this entire set of vertices. Right? So what I really want, let's say I want X bar. I want the vertex set of J to be equal to X bar. This is what I want. Yeah? Okay, so let's continue. Let's continue thinking what this means. And the three edges leaving X bar, where should they go? They should go to the barrier. So therefore, where should these three vertices be? These three should be in the barrier. Okay, so I should have three edges like this. These should be my three edges E1, E2, E3. And because this is my x bar, by adjusting notation, these are V1, V2, V3. Let me just draw them as well. And therefore the U1, U2, U3 are these vertices. This is what I want. Okay. So this is the situation we are hoping for, right? We want to prove that something like this is happening. Of course, this choice of U1, U2, U3 being here and V1, V2, V3 being here, that is just notation, right? This is the picture we are looking for. Okay. So let's do one thing. Because this is a tight cut, let's also make use of the fact that the two contractions are matching covered. Is that okay? So what I will do is I will shrink this into a single vertex. That seems natural, right? If you are hoping for this kind of drawing, it also seems natural that I would shrink this odd component into single vertex. That just means that I am shrinking x bar to a single vertex and I am looking at the corresponding C contraction. This is my cut C. Right? So C contractions are the two graphs, G shrink x and G shrink x bar. Let's make a drawing of G shrink x bar. Maybe I'll make a drawing of both. So when I shrink x bar, my x is as it is, x bar is this vertex, and I will get these three edges. We use the same labels of edges. Generally, when we take contractions, we don't give these edges different labels. That is just unnecessarily confusing and is additional notation for no benefit. So what we will do is, we will use the same labels of edges. These are the three edges E1, E2, E3, and these three vertices we will use the same labels. U1, U2, U3. This is our vertex, little x bar. So this is the graph G1 where I shrink this into single vertex. Yeah. Let me also draw G2 for the sake of completeness. So this will be little x. E1, E2, E3, and I get V1, V2, V3 here, and this is my graph G2 where I have shrunken x into little x. Yeah? And observe that when I splice these two graphs according to the obvious bijection, I will get this graph. Yeah? Okay. So now what I want to do is, I want to make the same drawing where I shrink x bar to single vertex. Yeah. I put 5 vertices, so let me put 5, why not? And now this is a single vertex. It is going to be little x bar. It is going to have these three edges, E1, E2, E3. These are U1, U2, U3, and I'm going to have, yeah, this is just another drawing of which graph? G1. Yeah, this is what we want. Remember, we don't have this. We want this. We want this, therefore we want this. Yeah, we haven't proved anything. Everybody with me? Do you all agree I have not proved anything? Good. Alright, so now let's try to understand what this means in G1. What do we want in G1? We want in G1 a barrier that contains U1, U2 and U3. All three, we want them to be in the barrier. Yeah? Okay. So, we would like to prove something like this. I don't know, I'll just write here maybe. G1 has a barrier containing U1, U2 and U3. We haven't proved anything. I want this. Yeah, okay. You all agree? If we prove this, then we will get this drawing. And then of course x bar will be an isolated vertex because it can't be in the barrier. Barrier is stable set. This is a matching covered graph because this is the tight cut. So the contractions are matching covered. Let's remember that. G1 and G2 are both matching covered graphs because it's a tight cut. Yeah. So if we can prove that there is a barrier like this in G1, then x bar will have to be a trivial vertex because all its neighbors are here. It cannot be part of a larger component because all its neighbors are here. So if it is in this situation, it has to be the whole component. And then in the original graph, I will get this situation. And therefore, this is a barrier cut. I'll be done. You all agree? Yeah. So if you prove this, we are done. Yeah. So we want to get here. Okay. U1, U2, U3, all three being in the barrier. It's a bit too much to ask for at a first step. What we have seen so far in the course is something like there is a barrier containing these two vertices if and only if blah blah. We have not seen any statement like there is a barrier containing all three vertices. Right? So let's settle for something lesser in life. Let's see if we can prove that there is a barrier containing U1 and U2. Can we prove that? Yeah. So, and then we will try to see if you can somehow push this U3 fellow into the barrier by using some standard tricks. Yeah. So, instead of proving this statement, I want to prove a weaker statement. Weaker. Let's try weaker. G1 has a barrier containing U1 and U2. Is that okay? Shall we just go with that? G1 has a barrier containing U1 and U2. Again, we haven't proved anything. We want to prove this. Yeah, this is what we want to prove. Okay, let's see. But by the way, do you all agree that this is sort of symmetric? G1 has a barrier containing U1 and U2. Instead of that, maybe I can also try to prove G2 has a barrier containing V1 and V2. Right? It's all symmetric. Right? Okay. Supposing neither of them has a barrier containing U1 and U2 or containing V1 and V2 respectively, what does that mean? Let's suppose that G1 does not have a barrier containing U1 and U2 and G2 does not have a barrier containing V1 and V2. What does that mean? To not have a barrier containing two vertices, what does that mean? G1 minus U1 minus U2 is matchable. Yeah. And similarly, G2 minus V1 minus V2 is matchable. Right? If both of these are true, then I will not get such a barrier in either of the graph for the corresponding vertices. Okay. So let's suppose both of these graphs have a perfect matching. Suppose that G1 minus U1 minus U2, now we are actually going to prove something. Okay. G1 minus U1 minus U2 and G2 minus V1 minus V2. Supposing both of these are matchable. Supposing both these graphs are matchable. And here the choice is actually important. I chose U1 and U2 and I chose the corresponding V1 and V2. I did not switch it to V2 and V3. Okay. So I am keeping the same to IJ. Supposing this is true, I claim this actually leads to a contradiction. Think about it. This should lead to a contradiction. DIY, quick DIY for now. Find a contradiction. Then we'll proceed further. And if you have figured it out, raise your hand, I'll comment out to you. Anybody else? Right? You should get a contradiction to some assumption. Tight. Okay, fine, that is a hint. You should get a contradiction to the tightness of the cut. Yeah? If you already got it, great. Let's wait for the others to get it. Assume that these two graphs are both matchable. Assume that when I delete u1, u2, I have a perfect matching in g1. When I delete v1, v2, I have a perfect matching in g2, what remains of g2. Right? So I have a perfect matching here in this graph after deleting u1 and u2. So I will circle them. Those are the exposed vertices. Similarly, I have a perfect matching here after deleting v1 and v2. Now what we want to do is we want to contradict the tightness of this cut in the original graph G. This is our graph G. Yeah, do you all see it now? Yeah. Okay. Yes.
I was confused. They can be adjacent also.
Yes, they could be adjacent. Yeah. I mean, I'm not contradicting that they're adjacent. I'm not making any argument about that. Of course, if you find a barrier containing the two, that means they are non-adjacent. Right? Yeah. Yeah, so you all agree? This cannot happen. Both of these graphs cannot be matchable. At least one of them is not matchable. Not matchable means you get a barrier in some graph. Yeah? Okay. So, contradiction then. Contradiction to tightness of the cut C. So this is done. So let us assume without loss of generality that one of these two graphs does not have a perfect matching, is not matchable. So of course, based on my earlier goal, I will assume this graph is not matchable. Yeah, adjust notation, or if you like without loss of generality, this graph is not matchable. Yeah. So therefore, it follows that G1 has a barrier containing U1 and U2. Now we have proved something. Yeah. But that's not what we want. We want a stronger thing. We want a barrier containing U1, U2 and U3. Okay, let's see how to get there if we can. Right. So let's make a barrier in G1 containing U1 and U2. So maybe I'll erase this drawing. This is where we want to get, but I don't have it yet. So this is my graph G1. There is some barrier. Let's call it B for now. This is B, and it contains U1 and U2. We don't know where U3 is. Yeah. So this is a situation in G1. Yeah. Now of course we want to ask, there are two interesting vertices here, X bar and U3. Those are the two interesting vertices. Those are the only two I've labeled. So where? Okay. So where are these vertices? What can we say about X bar? Where should X bar be? Raise your hand if you have figured it out. Right. So if you have figured out, so my question is, we want to prove this. Where is X bar? Okay, I'll come around. Can it be anywhere, or can it only be in some places? might be multiple ways to finish one. So let's see. Okay, so where is X bar? Or where is it not? So can it be anywhere or can it only be in some places? Right, and the thing you want to use is that G1 is a matching covered graph. G1 is a matching covered graph and we are looking at a barrier. And we know some nice things about barriers in matching covered graphs. So based on this, what can you say about X bar? No, just think about X bar first. Don't mix up with U3. Okay? Yeah? Yeah. Barrier is stable, right? Everybody agrees barrier is stable. So since a barrier is stable, since every barrier is stable, X bar cannot be in the barrier. X bar must be in one of the odd components. Since B is, oh, not here. Since B is stable, X bar is not in B. Well, if it is not in B, it has to be in one of the odd components. Yeah? That's the only choice it has got. So therefore, I can draw some edges. These edges are there in my graph. Remember, this is the graph G1. So I have the edge E1, I have the edge E2. Of course, what we want is, we want a barrier containing all three. If we prove this, we are done. Everything is finished. Yeah? So the only question is now, where is U3? Of course, if U3 is here, then we are done. Right? If U3 is here, then in fact, if U3 is here, let's just do it for a moment. If U3 is here, then we actually know this is a trivial cut. This is a single vertex. There can't be any more vertices in this component because it is a component, right? And then this is your desired barrier cut, which is what we are trying to prove, right? In the original graph, this will be your C, right? So if this happens, we are done actually. So what could happen, unfortunately, in life, is U3 could be here. Right? What do we do in this case? So there may be multiple ways to finish the proof from here, right? But this is the case we need to deal with, right? Now the question is, how do we choose to deal with it? So think about it, and if you have any ideas, I will come to your place and talk to you. You have an idea? Now I'll be able to understand. I see. Your claim is that if you include the three, you will again have a barrier. Because there's here, X bar will become isolated vertex. As a result, you will take over. Yeah. Okay. Any other ideas? Why can't there be more edges going from the component to the barrier? I'm drawing two edges. There could be a third edge, right? Not exactly. Since it's not exactly. Maybe there's a way to prove it, but I don't see it. Okay. Yeah, any ideas?
Not yet.
Not yet? Okay, think about it. So there are at least two ways to finish the proof from here. One I read in the morning and one I learned right now. They are essentially the same, just slightly different ways of saying them. One is, yeah, in some sense the one that is used in the book is uses a slightly larger hammer than what you are using. But it is a hammer we have already discussed. So here is a hint. If an arbitrary barrier doesn't work, you get stuck with an arbitrary barrier, then try special types of barriers. I don't mean special barrier. Right? That's different. So see if you can work with a different type of barrier, more specialized, and then it might work. It helps to give some things labels. So let's give this a label. This is my component containing x bar. Right? We just have to show that U3 is here. If we showed that, we are done. If U3 is not here, then it has to be here itself, right? Because these are components. You can't have an edge going from here to here. That would contradict components. Right? So U3 is here. So U3 and x bar belong to the same component J. Right? Welcome. Anyone else? Yeah? Okay. Anybody else? Right. So this barrier is not the right barrier in some sense. Can we improve this barrier in some way? Right? Remember, we just want one barrier where this situation happens. U1, U2, U3 are in the barrier, and x bar necessarily will be an isolated vertex because of things you have already discussed after deleting the barrier. Right? So B is not the right barrier, but maybe there is a better barrier. Right? And there are two ways to define a better barrier. Either you use B to define a better barrier, B star, or you just change the definition of the barrier B in a convenient way, and then everything works. Right? So any other ideas, any other suggestions?
Either maximize B or
Okay.
maximize the barrier.
Okay, so see if you can finish the proof. Right? So you have an idea, see if you can complete the proof from there. Right? Any others? Yeah. Okay, so I'll remember the only type of barriers we have discussed so far, apart from barriers themselves, we have discussed special barriers and maximal barriers. Right? So, can you finish the proof using maximal barriers? Right? Maximal barriers have some nice properties, better than usual barriers, general barriers. Right? So, what is the property of a maximal barrier? If you delete a maximal barrier in a matching covered graph, then what can you say about the components? Hypomatchable, factor critical. Yeah? All the components are what Lucchesi-Murthy call critical. Critical means you delete any vertex, the remaining graph should have a perfect matching. So if we take B to be a maximal barrier, if there is a barrier containing U1 and U2, then naturally there is also a maximal barrier containing U1 and U2. Yeah? I just take the largest superset of it. Yeah. In fact, we also know that the maximal barriers partition the vertex set. It's even nicer. So there is going to be a unique maximal barrier containing U1 and U2. Right? So if we take a maximal barrier instead of just a barrier, right? Then now look at this component. This should be hypomatchable. Is it hypomatchable? It's not hypomatchable, right? What's the issue? Which vertex can you delete and the remaining graph will have no perfect matching? U3. If you delete U3, X bar is isolated in this component. X bar is only 3 neighbors. 2 of them are sitting here, the third one is here. So if I delete U3 from J, then there is no perfect matching. Therefore, this is not hypomatchable, contradiction to maximality. So that's one way to finish the proof. Right? So this, if we do this, then we get, if we take a maximal barrier, then the maximality actually implies that U3 belongs to the barrier. And we are done. And we are done all the way. Yeah? The other possibility, if you don't want to use maximal barrier, turns out you can do something in some sense simpler. You can just say, take B union U3 and argue that B union U3 is a desired barrier. So you have to basically think why B union U3 is a barrier. So this is one option. Alternative 2 is to argue that the original B without maximality, maybe let me call this, B, not necessarily maximal. In fact, it should not be maximal. Plus U3 is also a barrier. If you don't take B to be maximal, then just add the vertex U3 to it. And argue that again you will get as many odd components as you want. So here I have 4 vertices. No, I think I had 5 vertices. I have 5 vertices here, for example, and I'm going to throw this 6th vertex inside this barrier. These are going to be still odd components, you all agree? I will still get 4 odd components. Now X bar will have all 3 neighbors in U1, U2, U3 because I threw U3 here. So therefore X bar is an odd component by itself. So I got 4 plus 1, 5 odd components. Therefore by parity I got 6 odd components. I don't even need to worry where the 6 odd component is. Right? This is a very useful trick in matching theory. Once you delete k vertices and you get k minus 1 odd components, the kth odd component comes for free. Right? So just use that. Don't try to worry about where is that component. Wasting time. Yeah. Okay. So these are 2 ways to finish the proof. Either you just take a maximal barrier and then it follows that U3 is in B, or if you don't do that, then you just argue that B plus U3 is also a barrier and that is the desired barrier. And this one will be not only a barrier but a desired barrier. Immediately gives you the conclusion you want. C is a barrier cut. Yeah. So therefore we have finished the proof in 2 different ways. Well, the ending in 2 different ways. Okay, so that's all for today. We have proved that, so I want to just conclude by a few remarks. We proved that type 1 cuts and type 2 cuts are barrier cuts, that was easy. Then we proved a relatively non-trivial result that type 3 cuts are also barrier cuts. And we used a bunch of things that we have discussed so far in the course, right? We used the stability of barriers, we used the maximality of barriers, and we used the fact when does a barrier even exist containing 2 vertices, etc., etc. And of course, in the very beginning, we contradicted the definition of tight cut to assume this statement that one of these graphs does not have a perfect matching, right? So we used all of these things. So that means that the interesting examples of 2 separation cuts should have at least 4 edges. Otherwise, they are just going to be barrier cuts, right? And we saw an example last time, which is in Lucchesi-Murthy. We saw an example where you have a cut that is a tight cut, but it is neither a barrier cut nor a 2 separation cut. That example has 5 edges. That standard example has 5 edges. So my question is there an example with 4 edges? I don't know the answer. Right? So is there a tight cut? Is there a tight 4 cut that is neither a barrier cut nor a 2 suppression cut? And if you can't find such an example, then can you prove that tight 4 cuts are always either barrier cuts or 2 suppression cuts? Open problems to the best of my knowledge. Maybe they are answered somewhere, I don't know. Yep. Okay. That's all for today. And we will continue on Monday. Are there any questions or concerns regarding anything we discussed so far? Okay. If not, see you on Monday and have a nice weekend. Thank you.